In this video, we're going to look at how we sketch the tangent function. Now, tan is quite different from sine and cosine because remember that tan can actually be undefined. So, to examine why this is the case, let's take the value tan of pi on 2. Well, that's actually undefined, and we can see why when we imagine that tan is actually sine of pi on 2 divided by cos of pi on 2. So sine of pi on 2 is 1, and the cosine of pi on 2 is 0. So if we had to do 1 divided by 0, we realize that we can't do that, and that's why we have this undefined. So because tan is also periodic, we can imagine that every time we would get some integer multiple of pi on 2, and really it's only the odd ones, because if it was pi or 2 pi, that would be fine. So every time we get pi on 2, 3 pi on 2, 5 pi on 2, we're going to have an asymptote. And that's why you can see on the graph here that we've got asymptotes that are really quite periodic. So you might also notice that they're exactly pi units apart. So we'll just get rid of those. Now, being pi units apart, that tells me that the period is equal to pi. There's something else that you might notice, and that's this mean value here. The average value of tan x, or the basic tan function, is actually equal to 0. Now we need to call that the mean value because despite what it looks like, it is not a point of inflection. It's not a stationary point, and it's really important that we know that. So that's our basic tan graph. What we notice is with the very basic graph, we might think that the period is pi. We know that the asymptote, as a basic, just looking at it, are odd multiples of pi on 2. And we can imagine that each mean value is 0, which is also the x-intercept. So our mean value is 0. It occurs halfway between asymptotes. So if we're looking at our graph, and I'll just zoom in a little bit on it, we can see here that halfway between this asymptote and that asymptote, we have our x-intercept always. So that's true when we've just got tan x. And as we zoom out, you can see here that there are some key features. So the period is pi, we've discussed that. The range is going to be reals. Unlike sine and cosine, we're not bound by an amplitude. In fact, tan doesn't have an amplitude, and that's not meaningful to refer to. The vertical asymptotes happen at all the odd values of pi on 2. So remember that 2k plus 1, just like when we revisited this with 2n plus 1, that's going to give us all the odd numbers if k is an integer. So what we're saying is, imagine k equals 0. Well, 2 times 0 plus 1 is 1. If k equals 1, 2 times 1 plus 1 is 3. If k equals 2, 2 times 2 plus 1 is 5, and you get the idea. So we know that whatever's inside, that tan x, that x value can't be an odd multiple of pi on 2. That's all that's saying. We know that asymptotes, just like intercepts, just like mean values, they're all placed one period apart. And with the very base graph, we can see that the x-intercepts occur at k times pi, because they occur at 1 pi, 2 pi, 3 pi, 4 pi. The domain is a little bit harder to say. The domain is going to be reals except anywhere that there is an asymptote. And so that's all that's saying there. Remember, we define the asymptotes up here. We've used an n instead of a k, but that doesn't really matter because we know that n is just those integers. As a side note, it's many to one correspondence. That means there are many x values which would give you the same y value. So now what would happen if we had a completely transformed tan graph? So remembering that this a out here is our dilation from the x, our n over here is our dilation from the y, and we have our translations h and k from the x and y respectively. So if we've got something totally transformed like this, a general rule of thumb is that our period is pi on n. It's a little bit different to sine and cosine because it's not 2 pi on n, it's just pi on n. The vertical asymptotes occur when n outside of x minus h equals 2k plus 1 pi on 2, where k is an element of the integer field. My God, that's a complicated sentence. And it's really difficult to understand what that means. But all we're really saying is, take the inside bit, take whatever's inside here, and say that that can't be equal to pi on 2. Or rather, the asymptotes will occur whenever that bit is equal to pi on 2. So remember that it will be true for all the odd values of pi on 2 as well. It'll be true when it equals to 3 pi on 2, 5 pi on 2, 7 pi on 2, etc. So one way that you could have a look at that is to simply think, okay, let the inside equal pi on 2, and then once I've found that out, I can just add a period each time. Because remember, I would have found the period as being pi on n. So the mean position will no longer be the x-intercept. Okay, the mean position will now be where y equals k. Now I'll show you why that's the case as we hop into Desmos. So here we've got the graph of tan x, because I've let a equal 1 so it disappears, n equal 1 so it disappears, and we're translating 0 units in the x direction and 0 units in the y. So we've got the base graph here. But as I alter the value of k, you can see that I'll be shifting this function up and down. And so when we say the mean value, that thing that looks very similar to a point of inflection, but definitely is not a point of inflection, that's going to be shifted up or down. It's what we call the mean value. And you can see that if I have a plus k, it's not going to be the case that the x-intercept is exactly halfway between those asymptotes. The asymptotes aren't changing, but the x-intercept is. So that's my proof for that. We'll pause that k there and just bring it back to roughly the center. Now we can have a look at what happens when I change the value of a. So if I change the value of a, we're not really changing our x-intercept. We're not changing our location of asymptotes. But once a becomes negative, you can see that the gradient is also negative. So another way to think about this, gradient's not a great way to say that. In fact, once a is negative, we'd say it's been reflected about the x-axis. So it's important to note that this value a doesn't really give us much information. Yes, it dilates and stretches out the graph, but the important thing here is just to note, is a positive or is it negative? It's not like sine and cosine. The amplitude, certainly, doesn't really have a meaning when we're talking about tan. Now we're going to show you what happens when we change the value of n. Now, to put this in context, if I start playing around with the value of h, you can see that I'm moving this graph, but I'm moving it left and right. I'm not really changing how far apart the asymptotes are. So we'll just bring that back to 1. Now, when I change the value of n, on the other hand, you're going to see that we're actually going to squash that in, stretch it out. We're physically changing where the asymptotes are. We're also reflecting about the y-axis, which, if n is negative, it gives you the same effect as if a was negative for a tan graph. That is, it will look like it's going down with time. So this n value is very related to the period, and it will actually change what those asymptotes are. And of course we knew that because the period for tan is pi on n. So hopefully I've given you a good idea of what all these transformations mean and what they look like in practice. So remember, when we're saying the mean position is at y equals k, we're talking about that weird point of inflection type point, which of course isn't a point of inflection, but we're looking at the y value there, the height of that graph. The x-intercepts really don't have a neat little trick. If there was a plus k, we absolutely have to make sure we just let y equal 0 and solve for the intercepts. So let's give a few questions a go, and we can put this into context. So suppose we're asked to sketch the graph y equals 2 tan 3x. So I'm looking just up here. This is the graph I'm asked to sketch, and this is the domain I'm after. So immediately it might be handy to first start with what is the period. So the period is pi on n, which in this case is pi on 3. So between 0 to pi, I should be thinking that I have roughly 3 periods. Now, where will the asymptotes occur? So the period and the asymptotes are always a good thing to start with. Well, the first one would occur where 3x is equal to pi on 2. Because remember that will be a problem. That will create an undefined if I had tan of pi on 2. So if I divide both sides by 3, then x will be equal to pi on 6. So that's my first one. So let's start with what we know. I'll draw this out and we can move on from there. So I've drawn out my axes now, and I can think that that first asymptote will be at pi on 6. So I might just shorten that a little bit. There we go. And the next asymptote will occur a full period after that. So let's think, what would that look like? Well, x is equal to pi on 6 plus a period plus pi on 3. Well, pi on 3 is really 2 pi on 6. And so we find that x can't be equal to 3 pi on 2. Sorry, I mean to say pi on 2, of course. 3 pi on 6, which becomes pi on 2. So my next asymptote would be pi on 2. X equals pi on 6, x equals pi on 2. Now we may well have a third asymptote, so I better double check that. X also would equal pi on 2 plus a period. Well, the period is pi on 3. So if I try to add these together, I'll end up with 3 pi on 6 plus 2 pi on 6, and certainly that's 5 pi on 6. That's certainly within our domain. So I'm going to need to add that on as well. X equals 5 pi on 6. Just to give me something to work with, I'll extend this axis and fit a little bit more in the screen. Okay, so we've got our asymptotes. We now need to think, how could we find our x-intercepts? And our x-intercepts will always be wherever the graph equals 0. But one thing I notice is that this has no plus k. So rather than me trying to work out the solution, if it wasn't translated up or down, remember, just like tan x, the intercept will be halfway between the two asymptotes. So what would be halfway between pi on 6 and pi on 2? Well, if I add them up, pi on 6 plus 3 pi on 6, that gives me 4 pi on 6. And then I divide by 2, that's going to be 4 pi on 12, which of course is pi on 3. So I can find that this intercept would be equal to pi on 3. Another way to do this is to think about it in terms of half periods. Half a period added onto pi on 6 would have gotten me to my next critical point. So that's because it's halfway between the two asymptotes. So 1 period is pi on 3, half a period is pi on 6. So what we're trying to say is we can just go up in increments of pi on 6. So pi on 6 take away itself, of course, is 0. Pi on 2 plus pi on 6 is 4 pi on 6, otherwise known as 2 pi on 3. And finally, 5 pi on 6 plus pi on 6 gives me that endpoint of pi. So we're looking pretty good. We've got most of our critical points. All we need to consider is making sure we label the 0, 0 and the general shape of the graph. I know that my value for A was a positive, so the general shape will go up as it approaches that asymptote. Now, just to play on the safe side, I might just keep these tails nice and short. That way I know I'm unlikely to be marked down for shape. It's important that my endpoints are closed dots because I've got inclusive brackets, and I should make sure I label x, y, and y equals 2 tan 3x. So there you have it. I wonder if you can try and give part B a go. Pause the video and I'll go through the solution in a moment. Have a look for the A values, have a look to see if this would be reflected about the x-axis or not. You might have to take an n out as a common factor so that you can determine whether or not this has been reflected in the y, but also so that you could help find the period. Finally, make sure you pay close attention to the domain so we know we're only graphing what is necessary. Okay, so the first thing I might notice is that we have a negative here. So this shape will go down with time roughly. I then think, this needs to be taken out as a common factor. So I'll rewrite this as y equals minus tan 2x plus pi on 4, and this allows me to see that we've actually been translated to the left pi on 4 units. I need to take note that I'm only doing between 0 to 2 pi. That's why I've sketched this the way I have. So those endpoints will be critical to work out today as well. I'll note also that there's no plus k. So this tells me that I'm going to have a good time of finding my x-intercepts because I just have to add half a period. Looking at it here, my n value is 2, and my period would be pi on 2. My half period is pi on 4. So that gives me some good kind of understanding of what this graph will look like. Remember that I can't have this inside bit equal to pi on 2. So I'll try that now. 2x plus pi on 2 can't be equal to pi on 2. This is how I'm going to find my asymptotes. If I subtract pi on 2 from both sides of the equation, 2x can't be equal to 0, and if I divide by 2, x can't be equal to 0. So that tells me what my first asymptote is. I'll drop that down here, and I know x equals 0 is how I label that asymptote. Remember that I can add a period up until I get to 2 pi. So if I add a period, we'll put that here, that will tell me that x equals pi on 2. I add a period again, x equals pi. If I add another period, whoops, sorry about that, x equals 3 pi on 2, and my final period, x equals 2 pi. So there are all my asymptotes spread out one period apart. And if I think about my intercepts being a half period, or being in between those, so that's where my mean value will be, but because my mean value is 0, there's no plus k, I can just think halfway between will be the intercepts. So halfway between 0 and pi on 2 is just adding that pi on 4 to 0. So we're going to have pi on 4 and 0. Halfway between pi on 2, or think of that as 2 pi on 4 and 4 pi on 4, would be 3 pi on 4 and 0. Then we've got 5 pi on 4. And you can kind of see that pattern here, that we would have 7 pi on 4. So recognizing the pattern is going to save you a lot of time here. Finally, we did say that this is going to be a graph that kind of goes down as it approaches those asymptotes. So we're going to think this is what my graph will look like. So we've labelled all the critical points. We don't have to worry about endpoints because they were asymptotes themselves. Last thing to do is just to label the graph. X, Y, and put it anywhere where it might fit. We might make a bit of space here. Y equals negative tan 2x plus pi on 2. So looking at this next example, we might be thinking, in what way is it different from what came before? Well, first of all, the domain is a little bit more complicated. Now, we don't know that for sure, but you can see that this is an odd domain. It's not something like just 0 to 2 pi as we might expect. Further to that, we have a plus k. So now there's going to be a bit more work to find my x-intercepts, because I'll need to solve this equation. Give this a go now, pause the video, and I'll do the solution in a moment. Okay, just like previously, we're going to start by finding the period. The period is equal to pi on n. Now in this case my n is 2 pi, so pi divided by 2 pi leaves me with 1/2. So half of that, my half period, will be equal to 1/4. Now we can find our first asymptote. Remember, our first asymptote will occur wherever this inside is equal to pi on 2. So 2 pi x equals pi on 2. Now, if we divide by 2 pi, then x is equal to pi over 4 pi, which of course is just 1/4. So I'll get out my ruler and we'll say that the very first asymptote occurs at 1/4. Now, if we add a whole period, so if we add half onto that quarter, we'll get our next asymptote, which is 3/4. So we can just put that here. If I added one more half, I'd be bigger than 1, which falls outside the domain. So I'll leave it like that. Remember that this goes all the way back to -7/8 though. So I'm going to need to extend my axes just so I can include a bit more of the other side. Close enough. And I can work backwards to find these asymptotes as well. 1/4 minus a half is going to be -1/4. So I can drop that in here. If I minus another half, I'm going to be -3/4. My mean value is now going to be up at that square root of 3. So if I'm trying to think about the shape here, the mean value being at the square root of 3 helps me because that's halfway between these two. That's going to be 0. So I've got this mean value here, which is 0 root 3, and that's also my y-intercept. So looking at the graph, the value of 3 is positive, and I can think that my first shape will look something like this. My next shape is going to have that value of root 3 again, and my last shape is actually going to finish at root 3. Now how do I know it'll finish at root 3? Well, if I had 3/4, well actually it won't finish at root 3, sorry, because 3/4 plus a quarter would be 8/8. So it's going to finish just before then. So that's important for me to note. I don't know where it finishes yet, so I might just leave this one blank. Here, we're going to repeat, and we're not sure where this one finishes, so we'll leave it blank. So we've got our y-intercept, we've got our mean values, we've got our asymptotes. It's now time to find the x-intercepts. Remember, we can do this by letting y equal 0. So 3 tan 2 pi x plus root 3 equals 0. That means that tan 2 pi x is equal to minus root 3 on 3. 2 pi x is equal to the arctan of minus root 3 on 3. And if I divide by 2 pi, then x is equal to 1 on 2 pi, just clean that up, times the arctan of root 3 on 3. Now we can use our calculator to find that, and I'll bring that up now. So just bringing that up on my calculator, I'm making sure that I'm in standard and radian. When I press enter, I get 1/12 as my answer. So my first x-intercept is equal to 1/12. Now, as I do that, I'm looking at my graph thinking it's quite impossible, and I realise that of course this should have been minus root 3 on 3. So if we copy that down and put in our minus, you'll see that it's actually -1/12, which makes a lot more sense. So what we're saying is that this value is -1/12 and 0. we can find the rest of these intercepts just by adding on that period. So negative 1/12 plus 6/12 will be 5/12. And were we to add on another period, we'd get 11/12. So 11/12 is bigger than 7/8, so we won't worry about it. If we jump back here, negative 1/12 minus 6/12 gives me negative 7/12 and 0. So I still have my endpoints to do, and I'm going to use my calculator to help me with that too. So looking at the calculator, I've got 3 tan 2 pi x plus root 3, but my x value I'm trying to find as the endpoint, as that's 7/8. So here I'm just going to put in brackets, we'll say times 7 divided by 8. Now, when I do that, I see that I get root 3 minus 3. So that's going to be a negative number because, of course, 3 is bigger than root 3. Now, why did I do that? I now know that my endpoint is going to be 7/8 and root 3 minus 3. That gives me a good idea of what this thing might look like, because if I had to sub in negative 7/8, I'll find that it looks something like this. Now, using my CAS calculator, I'll work out that this is going to be negative 7/8, and this time it'll be 3 minus root 3. So it's quite a complicated graph, but we wanted to do something like this for your understanding. If you did have a CAS calculator for this, and turns out we did need one, you'd probably just sketch that graph using the graph function. As a little test of our understanding thus far, let's have a look at this question from the Jacaranda text. The graph of y equals tan x undergoes a set of transformations to form the graph shown. So what we're being given is this image, and we're saying that that image was y equals tan x. The question down here has said explain why there's no vertical translation among the set of transformations. So when I'm looking at this graph, how do I know that there's no vertical translation? It's because the mean value is still 0. Remember that the mean value should be equal to k. So you could expand this answer, and this wouldn't really be an exam question, it's more just for our learning, but we would say something along the lines of the mean value is equal to k. Since the mean value is 0, we know that k must have been 0, and therefore there was no vertical translation. But honestly, if you just wrote mean value is still 0, that wouldn't be a problem. It's asking us to state the period of the graph. Well, let's have a look at my asymptotes. For part B, I've got x equals pi on 4 and x equals 3 pi on 4. So what's the difference between those? Now some of you can already see it, but just so we have a way of doing it, the second asymptote minus the first asymptote will give me the difference. And so we know that the period must be pi on 2. Now that we know the period, and we know that it hasn't been translated up or down, can we form the possible equation for this graph? Now it says possible because this could have a value of a at the front. We wouldn't really know. Looking at it, it has to be negative, but whether it's -1, -2, -3, that's not going to necessarily be known unless we had this, which we do. Further to that, it could also be reflected because of the value n. Remember that looks almost identical. So it says possible, but as we go through this, you'll notice that there really is one way to do it. So let's start with our general equation. We know that we've got y equals a tan n x minus h plus k. Now, I know that the period was pi on 2. So if the period is equal to pi on 2, and pi on 2 is equal to pi on n, hopefully we can see there that 2 must be n. So immediately I can replace that with 2. Now, usually the graph of tan x, where x equals 0, the graph is also 0. And I can still see that that's the case. So h and k are also equal to 0. So right away, one possible equation for this graph is going to be y equals a tan 2x. So what's the value of a? Well, I know that this is also true. When x equals pi on 3, y equals root 3. So let's try it. A tan 2 times pi on 3 is equal to root 3. So a tan 2 pi on 3 is equal to root 3. And if I divide by that, a is equal to root 3 over tan 2 pi on 3. Now, tan of 2 pi on 3, think of that like pi minus pi on 3. So that's in the second quadrant. It's pi on 3, so it's going to be minus tan pi on 3, which is minus root 3 on 2. If we bring the 2 up, we realise that's negative 1. We find a is negative 2. Now that's not the answer, because remember the answer needs to be what is the equation of the graph. So to put it in context, y equals negative 2 tan 2x. So just in summary, what do we know about tan? Well, if we let the inside equal pi on 2, we'll find the x asymptotes. Now formally, what does that look like? It means that n outside of x minus h is equal to not just pi on 2, but all the odd multiples of pi on 2. So pi on 2, 3 pi on 2, 5 pi on 2. The way we notate that is 2k plus 1 pi on 2, where k is an element of z. We need to find the x-intercepts. Just like normal, let y equal 0, but this will be much easier if there's no vertical translation. Because if there's no vertical translation, we're just adding half a period to find each critical point. So the mean value, and this is the mean y value, will always be equal to k, where k is the vertical translation, not this k here. You might be wondering, why on earth did you not just use n? And the reason is that we normally always notate n as the dilation from the y. And so having an n equals an n, we'd have to use n1, n2, and that can get even more confusing. So this is a general solution for the asymptotes, but I prefer you to think of it as let the inside be pi on 2, and then just add a period after that. So that's tan.